You clicked because you want to know if PyTorch is actually fast. The reality is that most developers are leaving performance on the table without realizing it. You are likely running legacy code that forces your expensive hardware to wait on the Python interpreter. By the end of this video, you will understand exactly how torch.compile changes the game and why your current memory management strategies might be silently killing your speed. There is a persistent myth in the machine learning community that PyTorch equals fast. This belief comes from confusing the speed of model development with the speed of actual execution. When you write a PyTorch model in eager mode, you are using a define and run pattern. This means every single iteration of your training loop incurs massive overhead from the Python interpreter. The Python code has to be executed line by line, and for every operation, it must communicate with the GPU to launch a kernel. This creates a bottleneck where your powerful GPU spends most of its time waiting for the CPU to tell it what to do next. The problem becomes exponentially worse as your batch size increases or your model complexity grows. In legacy eager execution, every small operation, like a matrix multiplication or an activation function, triggers a separate kernel launch. These launches are not instantaneous. They involve context switching and synchronization costs between the CPU and the GPU. When you have a complex architecture with thousands of small operators, the cumulative latency from these launches can dwarf the actual computation time. This is why a model that runs perfectly fine on a small dataset can crawl to a halt when you scale up to production workloads. This is where the concept of torch.compile fundamentally shifts the paradigm. The tool, which relies on the Inductor compiler, changes how the execution graph is built. Instead of executing operations one by one as Python commands are issued, the compiler captures the entire forward pass and fuses operations into a single Cuda graph. This fusion eliminates the overhead of individual kernel launches. The GPU receives a streamlined sequence of instructions that it can execute with minimal interruption. The result is that the bottleneck shifts from model definition to memory layout and data movement. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. However, simply adding torch.compile to your code is not a magic bullet. The performance gains are nonlinear and highly dependent on the complexity of your architecture. For simple models with very few operations, the compilation overhead might actually make things slower. You might see negligible gains or even a slowdown. But for complex architectures common in modern large language models and transformers, the speedups can be dramatic. The compiler can reorder operations and fuse kernels across the entire forward pass, leading to 2 to 4 times the speedup in production workloads compared to eager mode. Here is the critical insight that most practitioners miss. The optimization engine of torch.compile forces a new focus on memory management. Even with a fused graph, if your tensors are not contiguous or if you are using inefficient memory layouts, the generated graph can suffer from fragmentation. This fragmentation negates the hardware utilization gains you worked so hard to achieve. Without explicit strategies like ensuring contiguous tensor handling or using quantization-aware compilation, you are still fighting against the underlying hardware constraints. The compiler can only do so much if the data is not laid out efficiently in memory. This shift requires a significant change in how you debug your systems. In eager mode, when something goes wrong, you get a stack trace that points directly to the line of Python code where the error occurred. This makes debugging intuitive and straightforward. With torch.compile, the code is transformed into a compiled graph that the Python interpreter no longer sees in the same way. The opaque nature of this compiled graph means that standard stack traces become useless for profiling. You can no longer rely on the familiar traceback to find your bottlenecks. Instead, you are forced to rely on low-level Cuda profiling tools and explicit memory snapshots to diagnose performance regressions. You might find that a memory leak or a fragmentation issue is causing the slowdown, but the error message will not point to the specific line of your source code. You have to analyze the memory usage patterns and the Cuda kernel execution times to understand what is happening. This is a paradigm shift that requires a deeper understanding of the underlying hardware and the compiled graph structure. It moves the engineer from a high-level scripting mindset to a lower-level systems optimization mindset. Consider the implications for your daily workflow. If you are building a new model, you might be tempted to write it in eager mode to get quick feedback. But if you plan to deploy it, you need to think about how torch.compile will handle it. The compilation overhead is paid once at the start of the run, but the benefits are realized over every subsequent iteration. For long training runs, this pays off handsomely. For short experiments, the overhead might feel like a penalty. You need to weigh the complexity of your model against the time you are willing to spend on debugging the compiled graph. The gap between eager and compiled modes is not just about speed, it is about how you interact with the machine. Eager execution feels like driving a car with a manual transmission where you shift gears for every turn. Torch.compile feels like having a sophisticated automatic transmission that anticipates the road and shifts perfectly. But just like any advanced system, it requires you to understand the mechanics to maintain it. If you do not manage your memory correctly, the automatic transmission will still stall. You must ensure your tensors are contiguous and your data types are optimized for the specific hardware you are using. This realization changes how you approach production-grade development. You can no longer treat performance as an afterthought. It must be woven into the design of your models from the beginning. You need to consider memory layout, operator fusion, and the potential for graph fragmentation as you write your code. The tools are there to unlock the full potential of your hardware, but they require a new level of discipline and understanding. The myth that PyTorch is fast is only true if you let the compiler do its work. Without torch.compile, you are leaving a significant portion of your hardware's potential on the table. The transition to compiled execution is not just a technical upgrade. It is a fundamental shift in how we think about machine learning infrastructure. It forces us to confront the limitations of the Python interpreter and embrace the power of low-level optimizations. As you move forward in your career, mastering these tools will separate the hobbyists from the professionals. The ability to optimize for hardware efficiency is what defines production-grade engineering. It is the difference between a model that runs in a notebook and a model that scales to millions of users. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.